using vector components. Adding vectors by components. Life is actually much easier if we have the components of two vectors. That's a little surprising because usually make it hard. In this case, the components of the sum are just the sum of the components. That is, add the x components to get the x component of the sum. Separately, add the y components to get the y component of the sum. Put sort of more formally, c vector equals a vector plus b vector implies that c sub x is ax plus bx, and cy is ay plus by, and vice versa. If these two equations hold, then so does this one. Notice it has to be both of them. If one of them doesn't, it doesn't really work. As an example, we have two vectors with the following components. Ax is 2, ay is 1, bx is minus 4, and by is plus 4. Have it draw c equals a plus b. Well, we can see here that since c is a plus b, then cx is ax plus bx, which is 2 plus minus 4, or minus 2. And cy is ay plus by, which is 1 plus 4, or 5. So I want to start here, maybe, and go up 5 and over 2. The sum looks something like this. As a confirmation, let's actually draw a and b and then show that they add to that. So let's make a green vector, and it will go starting at the origin. A goes over 2 and up 1, so it looks something like this. And then starting at that point, tip to tail, because why not? We like to make it here. Starting here, we want to go over 4 and up 4. So 1, 2, 3, 4. 1, 2, 3, 4. And up 4. 1, 2, 3, 4. So B looks like that. And we see that, not surprisingly, it already lines up with what we had said was C. All right, for each situation below, and there'll be several on different pages, determine the components of the resultant vectors. So you can do this sort of two ways. You could try drawing everybody out. So we get A, and then we're going to add in B. And then we're going to add in C. And then finally we add in D. And our answer turns out to be, from the origin, which is where we started, and going there, we end up with this. So we can see that kx is plus 2 and ky is plus 2. But that was annoying, or at least tedious, and we went around. Actually, you don't know because I edited it out, but I had two other errors I made as I drew the vectors. So we're going to do it a slightly different way. We're going to say that kx is ax plus bx plus cx plus dx. And if we sort of clear our vector, so let's clean up over here. And now pull out, let's see, ax, well, that would be this part. So that's minus 2. And bx would be this part. So that's plus 2. Cx is this, or minus 1. Oops. And finally, dx is this, which is plus 3. And we see that this is minus 2 plus 2 is 0, minus 1 plus 3 is plus 2, just as expected. And likewise, ky is going to be ay plus by plus cy plus dy. So we look here, And we say, well, AY is this part. So that's plus 3. And then BY is this part. So that's minus 2. CY is, well, this part. It doesn't go anywhere. So that's a value of 0. And then dy is this, which is just 1. And so we have minus 3 plus minus 2 is 1, plus 0 is 1, plus another 1 is plus 2. And we see, happily, that this guy is that guy, and this guy is that guy. In other words, they agreed. I know that took a little longer to do both ways. We can see the component way was much faster, and that was definitely a lot easier because we had a grid. If there had been things at an angle, things could have been really kind of messy. This will work in any collection. So if we look at here, we can say LX is minus EX plus minus FX plus GX plus HX. And we can look here and say, well, EX is, well, 0. It doesn't go anywhere at all. I guess we would have had a minus sign in front of that. We have a minus sign in front of FX. Well, FX points this way, so FX is minus 2. And then GX is this bit, so that would be plus 3. And HX is this little tiny guy, that's plus 1. So we have minus 0 is 0, minus minus 2. So this is plus 2, plus 3 is 5, plus 1 is 6. And then we can do the same sort of thing for the Y. And looking at our guy, EY is 3. FY is minus 3. GY is minus 2. And HY is, well, 0. So now we have minus 3 minus minus 3. These two have gone, become 0. Minus 2 is minus 2 more, plus 0. We are left with LY of minus 2. So we can do that by, let's do it by direct calculation. We're going to take minus E, so that's minus E. And we're going to add minus F. So minus F goes over 2 and up 3. And then we're going to add in G, which goes, this is going to be a little awkward. That's 1, 2. So we're going to go over 3 and down 2. That's kind of unfortunate. And then we're going to add in H, which is like this. Ugh. And we're going to get a thing which points sort of like this, which is at least believably, sorry, that's going to be that, which is at least believably 1, 2, 3, 4, 5, 6 over, and 1, 2 down. So we do at least get the expected 6 minus 2. Written up in multicolor, but maybe a little bit less obscurely. Here we go. Then we're asked to do the same thing for these scattered vectors as shown, but actually it's a bit of a trick question because notice that all the vectors are the same. AX is still minus 2, AY is still 3, etc. These are the same vectors, they've just been scattered all over the place, which means that we would end up with that MX is KX and MY is KY because of the sum of the same vectors. And likewise, NX is LX and NY is LY because they're all the same vectors. So just remember that the vectors don't need to be at the origin. They can be anywhere on the plane. Multiplying a vector by a scalar using components. If we have the fact that B is equal to some number times A, where this K is some scalar, something which is not itself a vector, then we know that the graphical interpretation is we rescale A. The component notation says that if this is true, then it's also true that Bx is multiplied by K, is AX multiplied by K, and BY is AY multiplied by K. And that really comes down to that how you think addition works. If we just keep adding things, we get the multiplication. Works out the same way. Not a big deal, but worth flagging. All right, this is that if we multiply a vector by a scalar, then each component gets multiplied by that same scalar. So looking at something like this, we would say, well, I could graph it out and do stuff, but that's kind of awkward. Or I could say that Py is 3.5 Qy, but we see that Qy is minus 6. So this is 3.5 times minus 6, which is 21. So Py would be 21. And finally, sort of a trig example. Alice is flying her airplane. At the moment she is directly over the school. She sees a shadow of her plane in a field whose distance from the school she happens to know is 1,800 meters, because I guess Alice knows local terrain. To sight it, she has to look down at an angle of 62 degrees. How high is her airplane? And this is really pretty close to a standard trig problem. We're going to say, well, by the theorem that a transversal of two parallel lines creates alternate interior angles that are the same. This is also 62. And I'm going to name the height h. And we can see that from the definition, the tangent of 62 degrees here is equal to the opposite side over the adjacent side, which for us is h over 1,800. So that means that h must be 1,800 meters times the tangent of 62, which, if you grind it out, turns out to be something shy of 3,400, but the sig figs rounds up to 3,400. So she must be at a height of about 3,400 meters.